Okay, cool. So first of all, let me just thank you so much for having me. I'm sorry I couldn't be there in person. It's a little bit of a haul across the pond. And I'll note being on Zoom, I can't really see any of you in the crowd, like get any cues or whatnot. So please stop me if there's anything, because you'll have to speak up. And also, I'm just going to assume you are all laughing at any jokes I make, even if I cannot hear them. So yeah, all right. So my name's Ben. I'm a third year PhD student at MIT in the IT group at Sloan. And today I'm going to be talking to you about some work I've been doing thinking about automation and the social scientific process. This is jointly done with Kei-Hong Zhu, who's a physicist at Harvard, absolutely brilliant, and John Horton, my advisor. He's an economist at MIT. All right. Oh, the slide's not progressing. Okay, so in this presentation, I'm going to give you a brief overview thinking about AI, automation, the social sciences, kind of as it currently stands as of today. I know I've got a pretty mixed audience in front of me, if I have to guess, in terms of, all of you having some sort of machine learning or AI background, but your, discipline associated with that, I'm guessing is pretty diverse. And I'm going to discuss with you the system we built, which can execute one run of the social scientific process without any humans involved, from hypothesis generation to analyzing the results. I'm going to share some results with you that we generate using our system, discuss validation, and think about the bigger picture slash why this is useful. All right, so let's get into it. Here is like a really simple version of, well, usually in these presentations, I would say social scientific process, but honestly, any scientific process. A researcher, comes up with an idea, they run an experiment, they analyze the results. Sure, this is a simplification, but any of you who are empiricists of any type have participated in some sort of this process. And there's been some really cool work thinking about how we can begin to, automate or enhance parts of these process with AI in the social sciences. And I'm going to go through each of them with you. So first, hypotheses. Well, I don't know what other presentations you've seen today. Maybe you've seen someone talk about this. I wouldn't be surprised. But assuming you haven't, automating hypothesis generation or building hypotheses might seem kind of abstract and like a difficult thing to conceptualize. But this could be really simple. You could just open up ChatGPT, Claude, whatever your large language model of choice is. I'm sure many of you have played with them, and ask them to generate hypotheses about some social scientific scenario of interest. And it'll do like an okay job. It'll come up with ideas that are pretty plausible. You could be a little more fancy with this and, give it a bunch of relevant papers if it has a large context window and ask it to generate a hypothesis. Or you could even like hook it up to some corpus or, Google Scholar or the internet or Elicit, if you've heard of that, and ask it to go find relevant papers about a topic that you give it and then have it come up with hypotheses on these topics. So that's been kind of one strand of research of automatic hypothesis generation. Another strand is, using kind of induction based on real world data to generate hypotheses. And this kind of using LLMs has taken on a flavor of showing an LLM different observations of some phenomenon and asking it to identify hypotheses that, potentially explain the difference. And then finally, there's other inductive methods using real world data that have kind of been explored more in the economics and econometrics literature, which for reference is where I'm coming from. So here's some papers, kind of using LLMs and large corpora to combine literature and search for ideas, and some other work that has taken sort of this inductive approach, including this top paper, which I think is especially interesting, which came out, I think maybe, well, it came out 2 weeks ago exactly. The date is saving me at the end of July, and it comes up with some brand new social scientific hypotheses, brand new in the sense that like we don't have explicit evidence for them, and I think it was in marketing literature that they're true or not, and testing them on human subjects led to results, which is it's pretty cool. And long story short, with all of this, it's kind of possible to automatically generate hypotheses. So next portion of our scientific process is running an experiment. And once again, this might seem abstract or weird, but we can actually do this by just playing pretend and saying that an LLM is a person in terms of using it for a prompt. And now I'm not saying this is, a perfect proxy for a human, but if you open up ChatGPT once again and prompt it to be some sort of person, say, here's me, it will give you responses that are kind of, maybe a little bit aligned with some of these attributes. And you could take this person And you could ask it a bunch of different questions that behavioral economists or psychologists or sociologists and the like might typically ask, their human subjects. Another thing you could do is create lots of these different agents and have them have conversations and interact with each other and simulate more complex environments. I'll note this is one of those points in the presentation where I'm presuming all of you are laughing at this slide, but I couldn't possibly know. But, just a witness to that. All right. So, as I said, there's been work coming out of Stanford running these large scale experiments, these large scale simulations with many agents interacting. There's been some work in behavioral economics replicating experiments that I've been a part of. And, I would say most excitingly and importantly is front running real world experiments with these LLM simulations. So what these papers have done, the one at the top also came out just a few weeks ago, is they find an experiment, a human subject experiment, or an idea that they know could not possibly be in the training corpus for some model because it either was not posted on the internet or it was, generated after the training date of the model. And they run these simulated experiments on the model and then ex post see what happens with the human subjects. And in these examples, which I think the top paper had almost 100, they show that the LLM experiments and the subjects are like extremely predictive of the results in the human subjects. And so once again, similar to the hypothesis generation, like it's possible to use these things to do informative experiments. Now, I'll note, and before I get this critique, which I always do when I present this, like this is not a panacea. There are many situations that have already been shown where large language models have been poor proxies for human subjects. And I think a cool place in this literature, which is really blowing up in the past year, is trying to explore the boundaries of when this is or is not successful. And I think the takeaway is that it can be successful, but it's not perfect. I'll move forward, and this is good enough to just know as I'm going through the presentation. All right. Finally, analyzing results. Well, one doesn't actually need to use AI or automation at all to analyze results. If one has like a well-specified hypothesis, like in a pre-registration, if you've heard of those in social science, data analysis naturally flows from hypotheses. For example, I can see right now that there's two sides of this room. If I had some sort of hypotheses looking at all of you that said that I think the left side of the room is taller on average than the right side of the room, the data analysis to test this hypothesis naturally flows. Like all you need to do is run a two-sample t-test because you're just looking at the difference between two means. Sure, there's lots of more complicated subgroup analyses or assumptions you might have about heterogeneity of variance and the like, but you can get a sense of testing this hypothesis from something directly implied by the hypothesis. All right. So what my group did, or me and myself and my co-authors, was we noticed that there's really exciting work happening in all three of these areas, and that it's possible to use AI to augment or automate portions of them. And so we wanted to create a proof of principle system to see how far we can push this automation. So that's what we did. We created a system in Python and using large language models that, given some social science scenario or topic, uses large language models to generate hypotheses, design experiments to test these hypotheses, generates agents like the ones I've showed you so far as subjects to, and then runs experiments on independent LLMs acting as these agents, then automatically collects the data and analyzes the results, all without humans involved in the loop at any step. I'm going to walk you through the system in much more depth now. Okay, so here is an overview of the system, and I'm going to go through each of these 7 sections one at a time. So the system starts by just taking in some natural language sentence. It could be about any social scientific scenario of interest, two people bargaining over a mug, a job interview, and then what it does is it generates hypotheses based on this natural language sentence. And it generates these hypotheses in a very specific form that implies statistical analysis to test afterward, which is extremely important, as I described earlier, because in order to automate anything, the earlier steps in some process must indicate what the latter steps will be, or the possible decisions that could be made in automation will explode. So we formulate hypotheses as structural causal models, which if you've ever heard of Judea-Pearl, which given that there's lots of AI people in this room, I'm presuming many of you have and know more about him than I do. He has these structural causal models, which are just, very simple in their basic form, as you can see on this page, models of cause and effect that can get extremely complicated. and they allow us to specify structure for this automation. What does it actually mean to generate a hypothesis as a structural causal model? Well, the system takes in the natural language sentence, as I specified earlier, and then it iteratively queries itself, asking what are relevant outcomes, y variables, dependent variables that might be of interest to this scenario. And if you just open up ChatGPT, I think this is GPT 4.0, and ask it to come up with ideas of things that could matter, it's really easy. It's very effective. It can come up with these many different things that might be important for two people bargaining over a mug or any scenario you can think of. And so the key point, what our system does, is it basically asks questions of an LLM iteratively, takes that information and builds hypotheses from it. So after querying what relevant outcomes might be, it then asks itself, what are some causes that might affect this outcome? Here, the buyer's budget or the seller's sentimental attachment to the mug. Next, it might ask, how do we operationalize these variables? Obviously, you have to measure things to run an experiment and identify causal relationships. Next, and arguably most importantly, it determines how it might induce variation into the structural causal model such to run an experiment to estimate the path coefficients for this hypothesis. So here is what the hypothesis looks like according to our system. Now, once the system has generated the hypothesis, it needs to generate agents like the ones I showed you earlier. These agents, they might have names, they might have goals, they could have anything you want. But the most important thing they need to have is they need to vary on the exogenous parameters of the structural causal model. So we see here, since we said that one of the hypotheses was that the buyer's budget would affect whether or not the deal occurs, that we want to vary the buyer's budget in different ways for different agents. And we have that here, the different possible variations. All right, once we have our agents, we need to determine how they're going to interact because we're going to literally simulate their conversations to try and be as accurate and ecologically valid as possible. Now, if we have two agents, a buyer and a seller in this working example I'm giving you, this is actually a very simple problem. There's only one way that two agents can talk, and that is by alternating back and forth. Okay, technically two ways, you could have either one of them start first, but as the number of agents increases, the possible number of orderings of agents speaking increases factorially. 3 factorial for 3 agents, 4 factorial for 4 agents, it goes on. So we need to have better ways to think about how we're going to structure conversations. And not only that, conversations aren't just predetermined by some order and then go into that order. There's like a probability distribution over speakers, which is impacted by, all sorts of things from personalities to power structures and you name it. And in our paper, we came up with like a menu of 6 ways that conversations could be constructed to begin thinking about these problems to, create our system. I'm not going to go through all of them here, but I just wanted to outline the problem to you and happy to talk about this later over email, or if you look at the paper, which I'll give you a link, we outline them in more depth than you could possibly ever want to know. All right, so once all of the different speaking orders have been determined, the system takes these agents and each possible permutation of them and has them go off and simulate conversations. So here are 2 simulations, one where the buyer's budget is $10, one where the buyer's budget is $40. And you can imagine all the other permutations of the buyer's budgets and the seller's sentimental attachments. And this is just a very limited example. And we get these transcripts of conversations that look pretty realistic. You might not be able to tell that they were, generated by AI, besides the fact that they're pretty friendly. A lot of these models are over RLH-deft into being friendly. All right, well, once the simulations are complete, the system needs to collect the data and figure out what happened. And this is actually a really easy problem to solve because we just have these transcripts of conversations. And LLMs are really good at handling text. So we can give the transcripts back to the agents or some third-party LLM and ask it to figure out what happened. Did a deal occur? And, the system can easily read these transcripts, answer that questions, and provide us with numerical results. And once we have those numerical results for the outcome variable, and we obviously have them for the X variable because we induced the exogenous variation in the experiment initially, we can estimate the paths on the structural causal model to understand the relationship between the cause and effect in our hypotheses. And for those totally unfamiliar with structural causal models, a very simple structural causal model is basically akin to a simple linear regression, where the variable at the base of the arrow is an x, and the head of the arrow is the y, and the path is the beta coefficient. Note that there is an entire literature exploring these things Pearl won the Turing Award for kind of designing the world around them, and they can get way more complicated, and they offer a lot of really cool properties, which we're hoping to take advantage of in the future. All right, now that I've kind of explained to you the system in depth, I'm going to share with you some results generated using our system. Here's a sentence I put into the system, literally nothing else, just two people bargaining over a mug. And the system, without any human involvement in the loop, generated the buyer and the seller as the agents that it thought would matter. It determined that the buyer's budget, seller's minimum acceptable price, and seller's caring for the mug would be interesting causes that could affect whether or not a deal occurs. It then determined that it would want to vary the buyer's budget with these 9 values, $3, $6, $7, etc. And after running 400 simulations varying these values, we find that a $1 increase in the buyer's budget causes a roughly 4 percentage point increase in the probability of a deal. And when we run the exact same values for the seller's minimum acceptable price, we unsurprisingly find that the exact opposite effect occurs. A $1 increase in the minimum acceptable price causes about a 4 percentage point decrease in the probability of a deal occurring. Finally, when we vary how much the seller cares about the mug by literally giving it these sentences and the attribute treatment variations to the agents, telling them how much they care about the mug. So we'd have, a seller with the endowed preference that it has high emotional attachment or no emotional attachment, that the more emotional attachment the seller has, the less it cares, the less likely a deal is to occur, also unsurprisingly. All right, so here's another example. And this is all I put into the system. A judge is setting bail for a criminal defendant who committed $50,000 in tax fraud. And the system determines that there's a lot more agents relevant here: a judge, a defendant, a defense attorney, and a prosecutor. And it determines that these agents have, a slightly more complex interaction. What it does is it has the judge be this kind of central agent and the 3 other agents alternating with it in a predetermined order. Obviously, still not a perfect simulation of a human conversation, but, more realistic. And a lot of courts kind of do alternate with the judge. All right, next, it's the proposed SEM that it thought would be a hypothesis, that the final bail amount is an interesting outcome. The defendant's criminal history would be one cause. How many cases the judges heard that day was another, and the defendant's level of remorse was another. And, we can see here how the values of the different variables are each varied. Here's the outcome, and here's the variations for the different X variables. So the defendant's criminal history is operationalized in previous convictions. The prior case count is the number of cases that the judge has heard that day. And the defendant's level of remorse is basically how remorsefully expressful they've been assigned to be. And what we find is that the criminal history does seem to have an effect on the bail amount. The judge's case count that day, which it's actually like a lot of debate in the real whatever judge literature. I'm not that familiar with it, but this is something that is hypothesized to matter, did not seem to matter. And then finally, defendant's remorse has a pretty large effect. The standard error is large. We might ramp up the sample size in the future to get more specificity on that effect. Probably matters. All right, so that's all interesting. You're probably sitting here wondering, assuming I've done a good job explaining, how does this match the real world? Is there any, external validity? So far, I've shown you a bunch of simulations with LLMs and no people. So, I'm going to take a domain where social scientists and economists in particular have done a ton of work on theory. And it's one of the one places where the empirics match the theory pretty strongly, and that is auctions. So this is what I put into the system. Although we did a little bit of fiddling, which I'll discuss. And one thing I haven't noted to this point is the system can actually accommodate researcher interference at any point. Like if you disagree with some choice the system has made about the variables, or you want to explore something else, you can easily, put in that difference. And all our code, including the system, is online for use. You just need to hook up an API and be willing to spend a little bit of money. So we put in this sentence about 3 bidders participating in an auction for a piece of art. The system decided that the 3 bidders and an auctioneer would be the relevant agents, and it chose a similar speaking order as to the legal situation in the previous example, with the auctioneer being the central agent and the bidders alternating. It then decided that each of the bidders' budgets or causes that might affect the final price of the auction. And what we did to interfere is we made each of these bidders' budgets the same possible values in all the simulations. So they varied between 50 and 350 for each bidder's budget for the entire simulation. And what we found is that, a $1 increase in any of the bidders' budgets is about a 33-cent increase in the final price of the auction. And this actually makes sense because this is an open ascending price with private values, which, if you're unfamiliar with this, is kind of like your classic auction from a movie. Do I have $50? Do I have $100? Is this auctioneer? And the bidders kind of match these values if they want to do it. And since the theory predicts here that the second highest bidder's valuation will be the clearing price, because the first highest bidder's valuation will not bid against themselves once we hit that, and each one has a 1/3 chance of being this marginal second highest valuation bidder, it makes sense that a $1 increase would cause a 33% rise in the final price. All right, I'm going to give you some more in-depth looks at this bidding data so we can really unpack what's going on. Here is a subset of the results from the simulations. The columns represent the bidder's reservation prices for bidder 3. The rows are the reservation values for bidder 2. The x-axis is the reservation values for bidder 1. The y-axis is the final clearing price, making each triangle one of the simulated auctions. And note, this is just a subset of the results so that it's easier to visualize. And when we look at how the theory predicts these results, the second highest reservation price amongst the bidders, it does an extremely good job of predicting them. It's very close. And this is something that has been seen in the real world pretty consistently. And when we zoom out and look at all the results, the second highest reservation price, indeed, is pretty darn good at predicting the simulated auctions in the triangles. But this raises a question. Why did we go to all this trouble if the theory just predicts exactly what will happen? And the LLM's probably read about this theory. If you query GPT and ask it, hey, do you know about auction theory? It'll give you a pretty good answer. So what we do is we provide a more complex version of this prompt. For each one of the combination of reservation prices, we ask GPT-4, which is, if I haven't mentioned, the model we've been using through all of this, although one could use any model, to predict the final price of the auction for each combination of reservation prices. And what we find is that it's not good. It is almost 2 orders of magnitude worse in terms of mean squared error in predicting the results from the simulated experiments than the theory. All right, well, human scientists are often not so great at predicting what's going to happen in experiments, but sometimes experiments can be useful in informing our predictions and understanding of our world. So maybe the experiments the LLM ran on itself can be informative. So what we do is we take that previous prompt and we ask it to make a prediction for each of the combination of the reservation prices. However, we also provide it with the fitted structural causal model, fitted on all the data points except the one we're using in that round to avoid data leakage, to make a prediction on what's going to happen. And what we find is that the predictions in red are systematically better than the LLM's naive guesses. They're almost an order of magnitude better. So what we see here is that self-experimentation generated information that could be useful for in-context learning for the large language model, and information that makes it closer to the theory that is written and done to be predicted for by humans. All right, why is this useful? What's the bigger picture? So what I've kind of showed you here is that there is cool work thinking about automated hypothesis generation that's been successful in generating novel hypotheses. And LLMs, although we don't know the boundary conditions, can be used to predict experimental behavior through simulation. And what our paper has shown is that this can all be tied together in one iterative loop. So I ask you to imagine you being a social scientist, whether or not you are, you having some sort of social scientific scenario of interest, and you want to run some human subjects experiments, but you have just so many different ideas you can test. So you take up one of these systems and you have it simulate thousands of experiments while you sleep, exploring hypotheses with easy to interpret design and replications. And if you disagree with some of the system's decisions while you're sleeping, you can go back and fiddle with them and come up with new ideas. And using this is a place to complement human subjects research, to be informative about new ideas. All right, why might this be useful more generally? There's a lot of there's a new AI mind-blowing thing, at least in my opinion, coming out every week from Anthropic or OpenAI and all those other big tech companies. And, I'm using these systems not only as my research, but to help me do things with my research, writing, writing code, thinking about ideas, lots of things. They're integrating into life a lot. And as they get better, we're probably going to want them to be good at handling interactions with us. And humans are complicated enough where, simulating experiments of how we might behave could be helpful to have them better interact with us. Additionally, a lot of social scientific theories are, marked by stylistic examples that are much less effective than auctions. And creating complex structural causal models might be a better way to have better predictions in social science, because currently social science doesn't do a great job of making predictions in new areas. So I should note kind of the next places we're trying to take this work is I'll be the first to note that none of the hypotheses I talked to you about today were even remotely interesting. Does a buyer pay more for a mug when they have a higher budget? Yeah, whatever. Anyone could have said that. And so we want to think about how we can, after taking this proof of concept, actually generate some interesting findings. Another thing we want to do is, make the system a little more iterative, create potential research loops, and potentially create much more complicated models of the world. As I said, Judea Pearl has actually outlined a really cool and expansive literature that we can use to create much more complicated models that are perfectly identified for estimation. And finally, a big kahuna is, can we figure out when these simulations are good and bad proxies for humans? This is pretty open question. I showed you a lot of examples where they can be exciting uses. I'm also biased because I'm excited about this stuff, but I can show you a list of papers where they're doing a pretty bad job of approximating humans in general or specific subgroups of humans. So we need to ramp up our sample sizes, and by we, I mean me and those in this literature, and try and more effectively outline when and where we can use these things effectively. All right. I think that's 25 minutes and 30 seconds. Here is a link to the paper. You can also find it on my website. And yeah, happy to answer any questions in this limited time or email me afterward. I'm pretty responsive. Thank you.
Thank you. And thank you for this talk. I think it was fascinating. We have time for, well, one or two questions, if there are any from the audience. Not at the moment. Well, there is one. I'll ask a question first because there's something that I was thinking about during your entire presentation, which is how do you deal with error propagation? I know that it's a big problem. For example, large language models trained on data that other models created in the past. It tends to eventually get worse and worse in performance. I'm thinking if you have this loop where a model creates a hypothesis, it does a thought experiment, and then it analyzes the results to update the hypothesis, and you run this in a loop, will you eventually just ramp up errors?
Yeah, I think I think that is a I think that's a I honestly, we haven't started building that. It's a good point. I think that it depends on kind of probably the nature of the hypotheses you're exploring. And I'm guessing it also probably wouldn't be too hard to add types of resets such that, you have another model kind of come in and evaluate, does this seem like it's getting out of hand and we need to start an XYZ situation? That's something we'll have to tangle with. It's probably a little more solvable than with these I know that there was a paper in Nature that came out a few weeks ago saying that the LLMs devolve when they're trained on their own data. That whole system kind of happens that whole training is happening under the hood black box, and so you can't really stop it from doing poorly if it's caught in some sort of degrading loop. But I think with systems like this where you're interfering more at the prompt level, it'd probably be easier to handle such errors.
Okay, thank you. There's a, oh, there we go.
Thank you. Very fascinating. A couple of things. This is a kind of a philosophical slash conceptual question first. So large language models, they don't have the concept of statement built in. So they don't have a truth value attached to any piece of data you give them to some extent. This is my understanding. So I'm a scientist interested in the extent to which machine learning can assist the discovery. So could you connect some of your efforts here to, let's say, computer assisted proofs? Say in mathematics, is there any relationship between the use of large language models and that type of endeavor? And then in a related theme, if you're educating someone in a discipline like mathematics, you often struggle over understanding what is it that's serving as a roadblock to understanding. So I'm just wondering whether these large language models could be used as pedagogical assistants for educators to generate hypotheses as to why particular students may or may not be grasping concepts.
I mean, I think so. Real quick, what's your field? Just for to have,
Mathematician.
you're a mathematician. Okay, so um, they absolutely could be used to do that. I should note that I think this is one thing to note, just high level, when we're coming in for any social scientist in the room, will be very aware of this, but you might not be. Like the state of social science is, there's like this huge replication crisis. There's these issues with fraud, um, and we have do a terrible job of predicting new results. So what I'm offering here is very imperfect and definitely will have some sort of statistical error rate. So like as you say, there's no truth metric. So like if we're looking for extreme perfection, like not going to be provided. But given kind of the current state of a lot of social science and its capacity to like predict and do research, we don't need perfect. We need like a bit better. So that's one thing I should say relevant relative to mathematics is kind of like the bar of entry is a lot lower. And then as far as like figuring out why a student is struggling with something, it absolutely could be useful. I mean, if you show a student, like if you just take some like empirical data of a transcript of you, a professor, trying to explain a concept to a student and the student not getting it, and you give it to the LLM or, five LLMs and you say like, this student is not understanding X, Y, and Z. Here's the mathematical problem. Can you please explain to me, can you please propose some ideas to me about why the student isn't getting it and, how they might better understand it? Just like you as a professor could easily do that. And I think it would give pretty good results. Once again, as you know, the truth telling thing, like it's not going to be perfect and you can't guarantee perfection. But, given how difficult it is to teach and identify where students are struggling and also like where social science would make predictions there, it would do a bad job. Like this potentially offers like a level up to do a little better than we have been doing.
Yeah,
So
thank
yeah,
yeah.
I hope that's helpful.
Very helpful. I mean, if one is thinking of a large class, maybe this is a more practical question. Teaching, say, 500 undergraduates a specific topic. If one had an active bulletin board where they're basically posting their queries or questions, would an LLM approach be useful to sort of filter that to discern these sort of
I
common threads of difficulty?
I would absolutely be willing to do that. I would say you would have to be a little empirical about it and identify the error rate, which would be non-trivial. But I like I used these LLMs to I've been like, I've actually been working on some real analysis recently to kind of buff up my economic modeling for some other projects. And I have been using LLMs to evaluate, my own personal homework and like
So I think we've got a project we can do together. I'll be in touch.
they can do proofs. They mess up, but they can.
Thank you.
Okay, well, let's thank our speaker again. Thank you for coming. And yeah, if anyone has any questions, now's the time to take a photo of this slide. Okay. With that, thank you and have a good day.